Hello everyone, welcome to our topic for today. It is application of, still we are in the applications of derivatives, specifically on curve sketching. Alright, so let us have the objective for this discussion. So we have only one objective for this discussion, that is the use of the first and second derivative test in determining relative and absolute extrema. We have here some definition for our relative extrema. Function f has a relative maximum value at a number c. Alright, so this is our c here. If there exists an open interval I containing c, so this is our open interval from a to b where c belongs to. So this is an open interval from a to b where c is within this interval, such that f sub c is greater than or equal to f of x for every x in the interval I. Alright, so this is our interval I from A to B. Alright, so this is the definition of relative extrema. So relative maximum value. So at this uh, value for C at this point. Right, so this is a relative maximum value of the given function. Okay, or if you have this combination of this and this line, we have an interval here from A to B. This is our interval I. So still we can consider this point as the maximum, assuming this is a continuous function class. Okay. Another definition is that a function f has a relative minimum value at a number c. So this is our c, and also this one our c. If there exists an open interval I containing c, so these are open interval from a to b that contains c as well as here, such that f of c is less than or equal to f of x for every x in I. Alright, so if you look at the previous definition for the maximum, okay, so the condition here is that if there exists an open interval I containing c such that f sub c is greater than or equal to f of x. Right, so when you substitute this value in the function where this c, so f sub c is greater than or equal to f of x for every x in the interval I. And so do we this here in this graph. And if you look at the other definition, so it's the opposite. No? F sub c is less than or equal to f of x for every value of x in I. So it means that if you substitute the value of x that is on this interval, all right, the value of f sub c is always less than f of x, less than or equal to f of x. So even if the number is here or it's somewhere here, so as long as it's in this open interval. And so do with this one. So we have the interval a to b, so open interval. So c here, f sub c, the value of the function at this point, f sub c less than or equal to f of x in every x along this or within this open interval I from a to b. Okay, so these are very important definitions that we need to remember and understand. So we're talking of relative minimum value and relative maximum value. So we're just comparing the value of f sub c with the f of x in the open interval I. Alright, Now another definition is if a function has either a relative maximum or relative minimum value at c, then the function has a relative extremum at c. So we call it relative extremum. Alright, so either relative maximum or relative minimum value at c, then the function has a relative extremum at c. Extremum from the word extremes, right? So maximum and minimum, either, no, either maximum or minimum. So we called it relative extremum. So the function has a relative extremum at c. Now, for example, here, so consider a function whose graph is shown below. So at what numbers does the function has a relative extrema? At what numbers? So these are the numbers here: 1, 2, 3, 4, 5, 6, 7, 8. And we mark the points as A, we have B, and C. So these are the extremum. Okay, so relative extremum, right? So either maximum or minimum, or relative minima, or really a relative maximum. So we call it relative extremum at C. All right. So from this illustration, so we have here the function has a relative minima at x equal to 1. So at x equal to 1, so you see here, it follows definition. What definition was that? Number 1 or number 2? So about minimum. Okay, and then it has an x equal to 8 is also a minimum, right? So we call it relative minima, relative minima, because the extreme points, these are minimums or relative minima at x equal to 1 and x equal to 8, and relative maximum at x equal to 4, which is at point B. Alright, so this is what we call the relative extrema. So maxima and minima, maximum and minimum. Okay, so that's the basic concept about relative extrema class. So we have here A, C. So these are called relative minimum points. So these 2 points colored blue. So these points, so they are called relative minimum points. Okay, and we have B, the green color point. So this is what we call relative maximum point. All right. Now we also have what we call critical number. So definition: if C is a number in the domain of the function f, and if either f prime of c equal to 0 or f prime of z does not exist, then c is called a critical number of f. Okay, so it's a matter of finding the value of f prime of c, whether it's equal to 0 or does not exist. So if you can find this situation or values of f prime of c equal to 0 or does not exist, then c is called a critical number of f. For example, determine the critical numbers of the function defined by f of x equal to x squared minus 8x plus 2. So what we're going to do is just solve for the f prime of x. So f prime of x using the differentiation rule. So we have the derivative of x squared, so that is 2x, derivative of 8x equal to 8, then derivative of 2 constant is 0. So that's why we have f prime of x equal to 2x minus 8. Now f prime of x equal to 0, meaning you have to find the critical number, you have to equate f prime of x equal to 0. So you can solve for the value of x. So equating this to 0, so 2x minus 8 equal to 0, then you can now solve for x equal to 4. So x equal to 4 is the critical number. Okay, so note that f prime of x is 0 when x equal to 4. F prime of x is 0 when x equal to 4. So when x equal to 4, substitute it here. So 2 times 4 is 8, minus 8 is equal to 0. So therefore, x equal to 4, x equal to 4 is a critical number. So, and there is no value of x that makes f prime of x undefined or does not exist. So only this value of x equal to 4. Alright, so that's our very simple example, no, to emphasize more on this critical number. Now another example, example number 2. So determine the critical numbers of the function defined by f of x equal to x to the power x to the power 6 divided by 5 minus 12x to the power 1 over 5. So again, our procedure here is to solve for the f prime of x. So differentiating with respect to x or finding the f prime of x. Alright, so the first term, so we apply the power rule here. So the power will go down, so we have 6 divided by 5 times x to the 6 divided by 5 minus 1, so that is 1/5. Alright, so minus, so again this is a power rule, constant multiple then together with the power rule. So 1/5 will go down times 12, so 12 over 5 x to the power, so 1/5 minus 1, that is equal to negative 4 over 5. Okay, then simplifying, so finding the LCD here, so we got this f of x equal to 6 times x minus 2 divided by 5x to the power 4 over 5. Now looking at the denominator, so in the denominator or the x in the denominator equal to 0, so what will happen? So the whole denominator becomes 0. So we have 0, 5 times 0 is 0, or we have x to the power 0 is 1. X to the power with 0 raised to the power 4 over 5, because the condition is that the base, the x should not be equal to 0. So since this is equal to 0, so this makes the denominator 0. So 5 times 0 raised to the power 4 over 5, that is 0 times 5, 0. So we have anything in the numerator divided by 0, that is undefined. Alright, so we have to take note that f prime of x is 0 when x equal to 2. When x equal to 2, so in this 2 minus 2, 0 times 6, 0. So 0 divided by anything here. So the result is 0. So therefore, x equal to 2 is also a critical number, because this makes the result equal to 0, because the definition of critical number is that f prime of c equal to 0 or f prime of c does not exist or undefined. Alright, so we have to look for those numbers that can make the f prime of x 0 or undefined, or both of them, not like this one in this example here. So there are two values of x that can make the f prime of x equal to 0, and the other one is equal to or undefined, makes the f prime of x undefined. Okay, so we can say that the critical numbers of the function f are 0 and 2. Okay, so that's all about critical number. And we also have a term called monotonicity. Monotonicity. So it's about whether the function is increasing or decreasing. Alright, so we have here some definitions. So the first definition, a function f is increasing on the interval I. So the same I interval, the open interval that we were talking about a while ago. So a function f is increasing on an interval I if and only if prime of x1 less than f of x1 less than f of x2 for every x1 x2 that is element of the interval open interval I such that x1 is less than x2. So from the illustration we can see here that with reference to the y-axis our x1 is less than x2, right, in both scenarios here. So from this picture, so this is our y-axis or x-axis. So looking at x1 and x2 or x sub 1 and x sub 2, we can say from this illustration, you know, both of this illustration, this one and this one, we can say that x1 is less than x2. So there, this is the condition here that x1, x2 element of the interval such that x1 less than x2. So the function is increasing if this condition is satisfied. That when you substitute the value of x1 to the function, f of x1, sorry, f of x sub 1 less than f of x sub 2. Alright, so if this condition is satisfied, then we can say that the function is increasing on the given interval I. So this is our interval, right? So this is our interval from x1 to x2. Okay, so that's the monotonicity first definition. The other one is if a function or a function f is decreasing. So the first one was increasing, right? So this is the picture of increasing. The other one is decreasing. A function f is decreasing on the interval I if and only if. So this time class is the opposite. That are f sub x sub 1 greater than f sub x sub 1 for every x sub 1, x sub 2, that is element of I such that x sub 1 less than x sub 2. So same condition class that x sub 1 is less than x sub 2, but this time when you substitute the values of x sub 1 and x sub 2, it makes f of x sub 1 greater than f of x sub 2. Alright, so this is the illustration here. So you can see that from both of these pictures, so still x sub 1 is less than x sub 2 on both pictures, right? So these are x-axis, these are y-axis. So from the y-axis, this is shorter, the distance shorter. From y-axis to x2, so longer distance. So we can say that x sub 1 is less than x sub 2. Here also, x sub 1 is less than x sub 2. So on both of these illustration, we can say that when you substitute when you substitute the value of x sub 1 to the function, so it makes the value of f sub x sub 1 greater than f of x sub 2, right? So we can see that in both of this picture, the function is, or the graph of the function is decreasing, right? From this height going to this height, also from this height going to this height. Okay, so this is a definition, you know, for monotonicity, that is a decreasing scenario. All right. Now, function f is said to be monotonic on an interval I if it is either increasing or decreasing on I. So monotonic, we call it monotonic, you know, from the word monotonicity. Monotonicity. So we call it monotonic. So if the function is increasing or decreasing, so we call it monotonic. To be monotonic on an interval I if it's either increasing or decreasing on I. So here from these illustrations, we can say that this one is monotonic function. Right? So determine which of the following graphs represent an increasing or decreasing function. So this is an example of increasing function. This is an example of decreasing function. This is an example of increasing function. And this is an example of decreasing function. All right. Now we have a theorem, no, in doing the increasing and decreasing test. So we have to use this following theorem. Suppose suppose a function f is continuous. So we know already what is a continuous function. Our lesson at the very beginning. So suppose a function f is continuous on the closed interval. So you see the symbol here. You use the bracket, no? That indicates a closed interval. This one, this indicates open interval. So when you speak of closed interval, the value a and b are included. But if you have this open interval, the value of a and b are not included. Okay? So suppose a function f is continuous on the closed interval ab and differentiable on the open interval still ab. Then for the first theorem, we have if prime of x greater than 0 for all x in the open interval ab, then f is increasing on the closed interval ab. Okay, so this is another way of determining whether the function is increasing or decreasing. So we have to look at the derivative. So take note, no, just to remember it quickly. So f prime of x is greater than 0, meaning the value of our derivative is positive. When you substitute all the values of x in the open interval a to b, so if you found out that the value of the derivative is greater than 0, meaning positive, so we can say that the function is increasing on the closed interval ab. Otherwise, so this is the opposite. If the value of the f prime of x is negative, meaning less than 0, for all x, no, for all value of x on the interval, open interval ab, excluding a and b, then f is decreasing, decreasing on the closed interval ab. All right, so we can use this also to determine whether the function is increasing or decreasing in the within the given closed interval. All right, we have what we call the first derivative test for relative extrema. First derivative test. So we will use the first derivative to test for the relative extrema. So we already know what is meant by relative extrema. So theorem. So let f be a function which is continuous at each number in some open interval ab. So again, when we speak of open interval, this is written in this manner, and it means that a and b are not included. Now, when you substitute values, you should not include a and b. Containing the number c, it means that c here is within this interval a to b. And suppose that f prime exists at each number in this open interval except possibly at c. Okay, function is continuous. All right, so we have this condition here we need to see. Then we have a. These are the two possible scenarios now after that opening statement of this theorem. So scenario a. So if, so assuming that these conditions are satisfied, function which is continuous and some open interval ab containing c, and suppose that f prime, the first derivative, exists at its number in ab except possibly at c, then we have here a. If prime of x is greater than 0, meaning positive for all values of x in some open interval having c as its right endpoint, and if, so right endpoint, so meaning we are considering this part here. All right, so this is our c, this is the point. All right, so we have this point here on the right of this because we're talking of f prime, so that is derivative, no, we are considering this tangent line, tangent at this point where our c is on the right side of it. And if f prime of x meaning the first derivative of the function is less than 0, meaning negative for all values in some open interval having c on its left endpoint, meaning so we are considering this point of tangency at this point. This is our tangent line. So this time our c is on the left of this point of tangency. Then f has a relative maximum value at c. So if you look at this picture class, so it's clearly indicating that this is our relative maximum value. Okay, so take note the condition here. If the first derivative is greater than 0, meaning positive, and c is on the right side, right endpoint, and if so change the sign for this part. Now c is on the left of this point of tangency, this tangent line, then we can say that this is the relative maximum value at c. Okay, so that's for A. Now for B, if prime of x is less than 0, so this is now the opposite scenario class. If the first derivative of x is less than 0, meaning negative for all values of x in some point or some open interval having c as its right endpoint. Okay, so we're considering this part here. So c on the right part of this point of tangency, where our tangent line is located. Okay, and for all values of x in some open interval, now the second condition is the first derivative is greater than 0, so meaning positive. There's a change. No? There's a change. If you look at in another perspective class, we can see that there's a change. There's a change from negative. This is negative. You can remember this now because we know that if the line tangent line is sloping downward to the right, so it means it's negative, right? So for this scenario, we can say that it's negative. Our derivative here is negative. Okay, so from negative, then we know that at this point, tangent line, the slope at this point is 0. So the negative, then 0, then positive. So it changes from negative to positive. So we have what we call the minimum value, relative minimum value at c. Okay, so the change, remember, to easily remember this. So there's a change of the sign, no? Sign of the first derivative from negative to positive. Okay, so negative or positive, so relative minimum value at this point c. The other one, the first one is there's a change from positive to negative because sloping the tangent line is sloping upward to the right, so positive ang value ng f prime of x natin. Then here, sloping downward to the right, so this negative. So there's a change from positive to negative, so it indicates maximum, no? Relative maximum at point C. Okay, so that's how to remember, class. Now we have here a procedure in determining the value of extrema of a function f. So the first one is you have to compute for f prime of x. Then the second one, determine the critical numbers of f, that is the value or values of x for which f prime of x equal to 0 or f prime of x does not exist. No? That's to determine the critical numbers. And the third step is to apply the first derivative test. So to determine the relative extrema, no? We have to apply the first derivative test. And now for our example, if we let f of x equal to 2x cubed minus 6x plus 1, now determine the intervals on which f is increasing and the intervals where f is decreasing. Also determine the relative extrema of f if any, if there's any. Alright, so our solution, right? So step number 1, we have to find the first derivative. So we're given f of x equal to 2x cubed minus 6x plus 1. So taking the derivative, so we have f prime of x. Alright, so this power will go down, multiply to 2, so let's become x. So the power here minus 1, so we have 2 here. So derivative of 6x is simply x, derivative of 1 is 0. So we write only 6x squared minus 6. So this is our first derivative. And the next step is to determine the critical number of f. So to do that, so you have to equate, equate f prime of x equal to 0. So equating when f prime of x equal to 0, meaning at critical numbers, or f prime of x equal to 0, meaning at maximum or at minimum point. So either maximum or minimum point. So the f prime, meaning the slope, the slope of our function of our tangent line is equal to 0. So that's why we have here 6x squared minus 6 equal to 0. So from here, we can solve for x. So solving for x, you transpose negative 6 to the other side. So that becomes 6x squared equal to 6. So divide both sides by 6. So we have equal to 1. X squared equal to 1. Then taking square root on both sides. So we have x equal to plus and minus 1. Alright, so we have two values for x here, at which f prime of x equal to 0. So these are the critical numbers. X equal to positive 1 and x equal to negative 1 as our critical numbers. Okay, so critical numbers 1 and negative 1. Now next step is to consider the intervals determined by negative 1 and positive 1. So you just draw the number line and determine you have, so where this is coming from. So we have here critical numbers, positive 1 and negative 1. So you just draw the number line class to help you find the intervals. Okay, so let's draw this number line. So we have here the 0, assuming this is our positive 1 here, and this is our negative 1. So we have here the intervals. So the intervals are this one. This is our negative infinity on this part here, right? And then we have here the this part, we have the positive infinity, right? So it means you have this interval, this open interval, which is on the left side, that is the negative infinity. Okay, so negative infinity, this is open interval class, so that's why we have negative infinity and negative 1. All right, so it means negative infinity not included, negative 1 is not included. And we also have interval negative 1 and 1. It means from here to there. So we have this interval here. Of course, this is our negative 1, and positive 1. And then we have the right side. On the right part, we have this other interval, which is, of course, this is our 1 here. So 1 and the positive infinity. Okay, so consider the intervals determined by negative 1 and 1. So that's the third step. Then after that, you just do this table, then determine the sign of f prime of x in each interval and apply the increasing and decreasing test theorem, as well as the first derivative test. Okay, so you see here in our first interval, negative infinity to negative 1, just find out the value of our f prime of x. So it means, class, you just substitute any values that is within this domain. So what is the values that is within negative infinity and negative 1? So we can have negative 2, negative 3, right? Negative 5, and so on and so forth. So when you try to substitute it in the first derivative, where our first derivative equation is this one. Okay, so this is our function here. This is our function. This is our function. Then you take the derivative of this function. So we have here f prime of x. So testing now the value of f prime. So when x equal to, for example, negative 2. So substitute here. So negative 2 square. So that is 4 times times 6, so 24. 24 minus 6, that is 18. So we have positive 18. So f prime is positive. So the condition here is that every value of x within the interval should be the same, no? For example, if x equal to say 3, so when x equal to, sorry, minus 3, so that is still belong to this interval. So when minus 3, so minus 3 squared, so that is 9. 9 times 6, 54. 54 minus 6, that is 48. So that is still positive. So that's why we generalize it here that f prime of x for this interval is positive. So in our theorem, so if f prime of x is positive, so we can say that the function f is increasing on this interval, right? So remember, if f prime of x is positive for all values of x in that interval, so it means that the function is increasing. So that's why we have here f is increasing. So this is our conclusion. And for x equal to minus 1, so for x equal to minus 1, we have to solve for the critical point. All right. So when x equal to minus 1, you substitute this value to the function. So when this is minus 1 cube is minus 1 times 2 is minus 2. So here 6 times minus 1, so that becomes positive 6. Positive 6 minus positive 6 plus 1, 7. Minus, this is negative 2, so that is 5. Alright, so we have 5 here. And now solving for f prime of x at x equal to minus 1, substituting this to the f prime because these are critical numbers, right? So we're solving for the critical points here, and we have to determine whether it has a relative maximum or minimum. Okay, so this is 0. Okay, so the value is f prime of x when x equal to minus 1. Okay, so when this is minus 1, so minus 1 squared is positive 1. Positive 1 times 6 is 6. Then 6 minus 6 equal to 0. So here we have f has a relative maximum value. This is 0. Negative 1, why is it maximum? We have here negative 1 on the left side of the origin, then you have f of x equal to 5, so above. Okay, so for using the theorem, so we have f relative maximum value on this part. Now for this interval, negative 1 and 1, so negative 1 and 1, so we just determine the value or the sign, no? The sign of f prime of x, whether it's positive or negative, or greater than or less than 0. So what are values that is within this negative 1 and 1? So you can assume 0. So when x equal to 0, so when this is 0, so 0 squared, 0 times 6, 0. 0 minus 6, minus. So we have therefore negative. Or you can substitute any values within this domain, within this interval. So that is always negative. So therefore, if this is negative, the f prime of x is negative. So we can say that within this interval, negative 1 and 1, then f is decreasing. Okay. Now for x equal to 1, or x equal to, sorry. So for x equal to 1, then solve for f of x, substitute this to this function here. So we have negative 3. Alright, and then solving for f prime of x, this is 0. Okay, so 0 are f prime of x, then we have here the value of the function is negative. So it means that f has a relative minimum value. F has relative minimum value at this point, at 1 and minus 3. So here we have relative maximum because we have our f of x positive, right? So here our f of x is negative. Now for this interval, 1 and 1 negative infinity, meaning on the right side. No? So solving for f prime of x, so what are values that is within this one and within this interval? So you can assume 2, 3, 4, and so on. So assuming 2. So when this is 2, so 2 squared 4 times 6 24. 24 minus 6 is 18, so that's positive. If you try 3, 3 squared is 9. 9 times 6 is 54. 54 minus 6, that is 48, so that is still positive. So therefore, on this interval we can say that the function f is increasing. Alright, so these are the summary using the theorems that we have discussed earlier. Okay, now sorry class, we still have some more, no? um, all right, it's just rewriting it. Okay, so we have here continuation, so we can therefore summarize that interval where f is increasing, from this picture. So increasing on this interval, we have negative infinity to positive, negative infinity, negative 1, so function is increasing. We also have 1 negative infinity, 1 positive infinity, f is also increasing. So we can say that interval where f or the function is increasing, so we have this interval in union with this interval. So both of them, both of these intervals, f is increasing. Okay, now for the interval where f is decreasing, so here, this part here. So for this interval, we say that we can see that the f is decreasing because the derivative is negative, so decreasing. Okay. Now relative minimum point. Relative minimum point is when you substitute the values. When x equal to 1, you have f of x equal to minus 3. So this point, coordinates 1 and minus 3, is the relative minimum point. Minimum, it's indicated here. F has a relative minimum value. So this is a minimum point. And we have the relative maximum point. So where is it? So that is when x equal to negative 1, our f of x is positive. So this positive value here, that indicates that the point is a relative maximum point. So therefore f has a relative maximum value at that point. Coordinates negative 1 and 5. Okay, so that's the summary of this part, class. Okay, so I think uh, that's all for this part. Now I will stop this video to shorten it. Otherwise, if I have to continue it, then we have a very long video. So I'll continue the next part on our next video. Okay, thank you very much. See you in the next video. Bye.